Hello. Are we? Yeah. See the desktop now? Everything seem okay?
Yep.
Okay. Let me get some things set up. Okay. Oh, let me get a file. Okay. So we've been talking about these examples using closures. So I want to go. We did a little bit about this one, and we just started with the one on sorting. Let me show you one thing though. Like here's the folder on closures. I added some JavaScript files to it to show you that that you can do closures in JavaScript. So it's kind of nice to see the JavaScript version versus the here's the simple make adder. This was the one we did in Racket. Okay, so there's the Lambda with a free variable X, which is closed over here. Okay, and here's what it looks like in JavaScript. Okay, the JavaScript is actually kind of nice and clean. Um, you have a function. You can kind of say really a function that returns a function. This function has a parameter y, and you see that that x is a free variable in this function. You see real clearly that x is a free variable, and it's closed by this. Okay, so JavaScript has a fairly nice way of writing that. Okay, and the same thing is for the if you compare the make counter. Okay. Oh, and yeah, let's see. Yeah, we did that already. And if you look at make counter, same kind of thing. Yeah, it's uh, this is mutating that variable in the closure. Okay, so this one's mutating the variable in the closure. Notice it's a lot easier to write that than over here because in Scheme, you're not mutations kind of frowned upon, so you have to mutate it and then return it separately. It doesn't. You can't. The mutation operation doesn't return anything, so you have to mutate it and return it. Here, you can just pre-increment it and then return it. Okay. So the syntax in JavaScript looks very clean. It's a fairly clean. You just have a function inside of a function. Here we see it as a lambda inside of a lambda. Okay, right? So okay. Now I'm not using lambda notation over here. See, I'm saying function, and there's the name of the function, and there's this parameter. Here I'm saying here's the name of the function, and the function is a lambda. In a minute, I'll switch to I could write the JavaScript using lambda notation. Actually, let me go ahead and change it. Well, let me see if I remember how to write it in lambda notation. I think you just say make counter equals. So make counter is the variable. The variable's value is n goes to. That makes it a lambda. I don't think I need the return. I don't need the function. Then I need the empty parentheses to say that there's a function that goes to n++. I think that's right. Okay. Notice I abbreviated a lot. Now I'm using a lambda notation. If I wrote this syntax right, I'm defining this variable. So I'm defining a variable. The value of the variable here is a lambda x goes to something. So the value of the variable is, if I want, I could change this. I used x in the other side, so I can use x here. X goes to something, and what it goes to is a function that takes no parameters. So this is going to it's returning a function that takes no parameters and returns the increment of x. Okay, I think that's the correct notation for the lambda version of the JavaScript. Then if I want to run that, I run it by double clicking on its HTML file. See, the site says 5. Okay. See, the site says 6. The site says 7. The site says 8. That's these alerts. Okay. So I was counting from 4. So I made a counter starting at 4. Then the count from 4, the first time you counted, it counted to 5, then 6, then 7, then 8. So if I reload this, it'll say, it starts off, after the first increment, count from 5. Then after the second increment, it's 6, then 7, then 8. Okay, so JavaScript actually has this, if you want to, see, if I go back, there's using the old-fashioned C-like notation of JavaScript. So now C doesn't let you nest functions, but this is giving you the old-fashioned C-like notation. And then here's the real modern Lambda notation. So here's both of them together. Okay. Okay. You can compare the old-fashioned C-like notation that JavaScript has, and then there's this more modern. This has been added. JavaScript is making itself look more and more like, essentially, really doesn't even look like Scheme. This actually looks more like Haskell. JavaScript has actually got a part of it now that looks pretty close to what Haskell looks like. Okay, so this notation turns into this very clean one-liner. So you notice that, look how much punctuation got rid of. The braces were gone, the keyword function's gone, the keyword return is gone. It's just my variable is a lambda expression. So this guy's defining a function that is a lambda expression. It takes in x and returns that. Okay, what is that guy? Well, he returns a lambda expression that takes in nothing and returns this, but this is the open variable that refers to, see, this is the lambda expression that's open, that needs a closure, because in this lambda expression, x isn't defined, so x points is actually the closure is that x there. Okay.
So you could shorten that,
Pardon me?
correct? You could shorten that by one level.
Oh, really? How? I need a
Um,
function that returns a function. So I don't think so. Make counter is a function that returns another function, like over here. Make counter is a lambda that returns a lambda. So I don't think it can be shortened anymore. And here, see, function make counter is a function that returns a function. You can debate whether, if you are not used to functional programming, this might be easier for you to read. If you're used to functional programming, this probably is going to be easier to read. Okay. And I can go back to make adder and do the same thing. Okay. I can give this a modern notation. Okay. make adder is a function. The function takes in one number and it gives me what? Well, it gives me another function. So that would be a function of y that returns what? It returns x plus y. Okay. Now, let me comment out that and make sure. So I'll comment out the old, keep the modern one. I run this program by double clicking on this loads the JavaScript into the browser. Okay, the site says 9. Okay, it didn't do much. So that was this one alert here, add 5 to 4. So I made adder. Now, actually, let me try something here. What happens if you alert add 4? Add 4 should be I mean, I'm not sure what JavaScript will report. You know, add 4 is a function. Add 4, well, it's a closure. It's the thing that got returned by make adder. So it's actually a closure. I'm not sure if JavaScript has a way of printing closures.
Haskell and R would just return the source code that sits
And
behind
that's what it
the
did.
function.
Look.
Yeah.
Yeah, it returned the source code. Cool. Yeah, add 4 is a function. It's the function y goes to x plus y. That's actually kind of nice.
Other than just transparency, does that have any practical use?
Well, no, actually, it's a little bit dangerous. It's actually, I would argue, almost dangerous. Notice, okay, think about, from our point of view, what is add 4? It's a closure. And the closure is two things, an IP and an EP. And this guy's only showing you the code pointer. So it's not pointing out where's, like look at that. You have to go, there's something wrong there. What is that? What's wrong when you look at this?
Well, I mean, arguably, that's not printing out a closure. That's just printing out a Lambda expression.
Right. But it's misleading, because when you look at that, what's the obvious question?
Where's X?
Where's X? See? And the closure knows where X is. In this case, in this one, X is 4, because this was add 4. So it's failing to show us that this is not actually an open expression. It's actually a closed expression where the X is bound to 4. So if they were really clever, they'd have some way of showing you the closure, which is what I think what they really, I mean, if they should actually kind of come up with, because from the point of view of educating programmers and making sure that programmers are aware of what's going on, this guy's not just a formula. He's not just y goes to x plus y. For example, okay, let me do something else. Okay, let me show you what I mean by they ought to be more careful. Let me define add 5. Add 5 will be make adder using 5 as the base. Okay. Then I can call alert add 4. Then I can do alert add 5 to 5. I could say show me add 4, show me add 5. Okay. Okay. Now run it. Okay. Excuse me. That alert is 5 plus 4. This alert is 5 plus 5. It's coming from line 12. Now watch this, lines 13 and 14. Y goes to x plus y. That's line 13. Y goes to x plus y. Something's not right. They can't be the same thing. Add 4 and add 5 aren't the same thing. Add 4 is closed by x is 4. Add 5 is closed with a different closure where x is 5. So they misleadingly just show you the EP, or the IP part of the IP-EP pair. They're showing you the code part of the closure, not showing you the closure part of the closure. And you can get very misled by this. See?
You could think that what you're printing out isn't actually a closure, it's still a lambda.
Yeah, you might think,
If
yeah,
you're debugging.
exactly. You think that's a lambda, but then you're going to scratch your head and go, where's X? And
Like, I
if
thought I
it's
closed that. Where's my closure?
right. And if it's a complicated program, you may not know quite where it's being closed. In a complicated program, you may not really know where the closure is. And also you just may not quite understand. You may think that X is a global variable, for example. Like, for example, I could do the following. Let me do something else here. X equals 1001. Okay, there's an X. Okay, go here, run it. Okay, X, 9, 10. Y equals X plus Y. Oh, that's this guy, right? See, how would you know what that X is? That X is not him. That X is him, but bound to 4, because this is coming from line 14. This is add 4 with that X bound to this X, bound to that X with the X equal 4. Then the next line, well, this is now add 5. This X is that X bound to 5, not 4 now. And neither of them are that X, which is, if you were a naive programmer who came from C and thought, oh, when you have an unbound variable, it's the global variable. For example, if I wrote this, then I can confuse the heck out of a C programmer. Okay, because a C programmer will go, oh, that X is the global variable X. But no, that X is the lexically closest X. This X is that X. It's the lexically closest X, so it's that X, not that X. Okay, but they only report the lambda out of the closure. They don't report the closure part of the closure. So you can get misled by this. Okay, I don't even know what it'd be interesting to kind of think of a notation. Like what would be a clever way for them to say what the closure is here? It'd be a little bit tricky. I've been trying to think of maybe like make language 8 do that. I was actually thinking about this the other day. Can I make language 8 like be more careful like than JavaScript is here? Like JavaScript is telling you which it's doing a nice job of it. It's elegantly telling you the instruction part of the closure, but it's ignoring like even if it just put a little like if it put a little annotation saying that there's a closure, maybe just even telling you there's another piece to this, just to remind you that that's only half of what this variable is. That this is only the half of add 4. Okay, actually I don't even remember which one we're up to now. I don't remember if this one is add 4 or add 5, but that's only the half of it. Okay. Notice that when you play around with different languages, every language is a little bit different. So like Scheme, if you go back to Scheme, and you go to Scheme and you ask what's add 4, or if you add, okay, if I update the Scheme version, I could, well actually if you do this, okay, what is add 4? Okay, now let me run that in Scheme. Scheme isn't going to give me something all that nice. Okay, so there's adder, make adder and racket. Okay, run it. Okay. Compare that to the JavaScript. Okay. How did Scheme report a closure compared to how JavaScript reported a closure? Okay, now we know what JavaScript reported to us. It reported just that part there. What does Scheme do? When I asked what's adder 4, well, it tells me it's a procedure. Okay. I don't know. Can we make sense of this?
It points out a line number. line
is that
5,
all it's
character
doing?
4.
Oh, so it's not even trying to do, it's more or less doing what JavaScript did, right? Let's see. It's line 1, let's see. 5, 4.
So here.
That line, that's the line number, but the 4,
1,
oh yeah, that's the very 1, 2, 3, 4. I mean,
4, yeah, that's right.
what? Okay, let's do something. Back it up. Oh, actually, I can back it up, run it, see if the yeah, 5, 2, line 5, character 2. So that's just the line. That's the line number and character number of the beginning of the Lambda expression. Okay, so it's giving you and it's not pointing out that, oh yeah, there's also a closure involved. So Scheme also kind of punts on the closure part of the closure. Okay, that's, and I think, if we did something more sophisticated in Scheme, it would tell us more. But right now, it's just saying it is a procedure, and it's telling us where it's telling us how to find the code for the procedure, but it's not telling us how to find the closure of the procedure. Okay, and JavaScript would just tell us. JavaScript would. Oops. Huh. JavaScript files are bound to they're bound to Windows scripting host, whatever that is. And it didn't like the JavaScript either. It is correct JavaScript. Okay. Okay. See, we just get the Lambda expression. Okay. Oh, I know what that is. Notice that this JavaScript file is by Windows default is assigned to something. It's assigned to something called Windows scripting host. And notice it's saying you got a syntax error on line 8 of the JavaScript. What could that be? We don't have a syntax error. You know why that's saying that?
That might be the end of the line.
No. Well, it didn't like line 16. Oh, I'm sorry. It didn't like line 8. Okay, line 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Get it? Didn't like the arrow. Here's what's going on. Windows scripting host is an ancient version of JavaScript that Windows still has built into it. It's an ancient version of JavaScript before they started putting these Lambda expressions into the language. So Windows, for some dumb reason, still has built into it an ancient version of JavaScript that they used to call JScript. It's actually, now I remember, it's called JScript. And it's run under something called Windows Script Host, which nobody uses anymore. Well, no, but it's still there because some company somewhere in the world is using it, and they want to run their old JavaScript code on it. Okay, so now when I double click on that, I'm running my JavaScript program under Windows Script Host, which is an ancient version of JavaScript, and it doesn't know the modern notation. In fact, if I go back and let me put this back to the old JavaScript and comment out this one. Now that's the old JavaScript. No, it didn't like my alerts. So maybe even alert is new. Maybe alert wasn't even in part of it wasn't part of this. But notice it got past that, and it didn't like the alert. Okay. Okay. So, but that's just kind of a quirky thing. Yeah, on your computers it might be the same. These JavaScript files, maybe on your computer they're also associated with Windows scripting host, but that just seems to be a default behavior of Windows from and Windows scripting. Now remember, it's an ancient version of of JavaScript from probably the early 90s. It's no, I'm sorry. Yeah, like the mid 90s. It's probably from the mid 90s. It was Microsoft's first attempt at JavaScript. Okay, and I hadn't even remembered that it's still there in Windows for whatever bizarre reason. Okay. Okay. All right. So notice how it's kind of interesting to play around with different languages. It's nice to take a piece of code and say, what does it look like in Racket? What does it look like in JavaScript? What does it look like in Java? You know, what does it look like in Java too? Okay, actually, you might ask Java to do the same thing. Here, system.out.println, add 4. Now, I don't know if there's a toString method for closures even.
Generally, if it's an object descendant, it's going to have
Oh
a
yeah, you're right.
toString.
All objects have, yeah, it is an object. Add4 is some, well, it's a, yeah, it is, see, it's a closure from our point of view, which somehow is going to be represented as some kind of object in Java. So it is, so it will have
something.
some kind of toString. Let's see what it looks like.
Complete nonsense. Okay.
No. Yeah, let's read it. Let's try to parse it a little bit. Okay. Add4 is a make adder. Okay, it is a make adder, so it's a make adder. And what is it pointing at? It points at a closure. We know that it points at a closure. So here it says it's a make adder with a lambda. So that means it's a lambda. Now, I would bet anything that that is the address in the heap of where the closure is. My guess is this stuff here somehow. Now, I don't know what the 2 is. It looks like there's a 2/something. Then there's at something. If I'd be worth maybe trying to dig through later on what this, but it looks like it's saying it's a lambda something / something at something. So my guess is somewhere in there is the address in the heap, possibly, of the closure. Maybe one of these is, it could be IPEP. Maybe one of these is a pointer to where the code is, and one of them is a pointer to where the heap is. So this might be like 2 pointers.
But one looks to be in decimal, and the other one looks to be in hex.
Yeah, but it might be a coincidence. I might be just barking up a wrong tree. I mean, yeah, this is how I analyze things. I make guesses and I try to verify them. Yeah, we know that it is a closure. We know what a closure is. A closure is 2 things. It should point to the code, which is this case is this code, and it should point to an environment that is the thing that closes it. Okay, there might be embedded in there, though, but yeah, I don't know. I'm just kind of wild guessing. But notice it's kind of fun to compare Java with Haskell. I'm sorry, Java with Scheme with JavaScript. How do they print out a closure? How does this one print a closure? How does this one print a closure? And how does this guy print a closure? You know, and those are interesting questions to ask. And that's the kind of experimental computer science. There's a nice way to think about computer science. Most people don't think of it this way, but it's an experimental science like chemistry and physics. You think of it, you create a hypothesis, then you write an experiment to try to verify your hypothesis. You write code and then you run the code and look at what you get out, and you try to figure out, is it verifying your hypothesis or not? Is it showing us the closure? Is it somehow showing us what the closure is? So this is an interesting way to deal with programming, is not just ask, how do I write something in the language, but try to dig into how does the language actually do it. Okay. Like if we do this in our language, the language 8, I wrote it so that language 8 prints out as much of stuff as possible. Like here's the language 8 version of it. Okay, and it lets us watch the execution. Okay, and I try to be specific. So like here, I am trying to say that makeAdder is an IP-EP pair. Okay, but I'm not showing you where the pieces of it are. That's what I was thinking. I wonder if I can make this a little bit better. Like here, I show you that in the environment, makeAdder is that. Okay, but that's just saying that it's an IP-EP object at that address in the heap. Maybe I can come up with a better way of printing that out so that it would be something combination of JavaScript prints out the code, but it doesn't print out the closure. So I'm wondering, maybe I can improve that to be a little bit more specific. Okay, like and if I our language, I could also have it print add 4. Okay. So I could say print add 4. I'm not sure what it's going to print. I don't even remember what it'll do. So here, the last part of the program is print add 4. Okay. So let me run it again. When I printed add 4, I got this thing, IP-EP pair. Okay. So can I fix that to be a little bit more informative? Like right now, since I have a pointer to the IP-EP pair, I could potentially print out the Lambda part of it and maybe somehow represent the closure part of it too. So maybe you can make this a little bit better than what either JavaScript or Racket does, or Java. Okay, so so the key idea is that we have to remember that a closure is two things, and we can't be fooled by the language. A lot of times people forget that it's two things, and that's one of the keys to understanding closures, to keep reminding yourself closure means two things. That's why I call them IP-EP pairs. Closure means two things. Closure means two things. And even though these languages will show them to you as one thing, you have to keep reminding yourself that they're really two things. Okay, it's real important. You got to be real careful not to just think that a closure is a Lambda expression, because otherwise you get into these pitfalls that why are these two different closures but they look alike? If they're two different closures, why would they look the same? And it's because half of the closure is not being shown to you. Okay, all right, let's do okay, now so that was adding some JavaScript. Now let's see, here's the currying stuff. And I did the same thing here. I added the JavaScript currying to here just so that you could do all the currying we were doing the other day. We could do it in JavaScript too. Oh, let me clean up this window a little bit. Okay. I did this because I realized how if you type your code in the modern, elegant JavaScript, it's even way better than Scheme is. Okay. Look, it's actually, if most of you probably never seen the Haskell language, but if you learn really ultra modern JavaScript, you can actually write code that looks surprisingly close to Haskell, really kind of elegant, simple code. Every one of these is just one line. So for example, this was a curried version of this function of 3 variables. And here's the function. I'm sorry. I think Oh, I opened the wrong file. These are, I'm comparing two things that aren't the same. I opened the wrong JavaScript file. I wanted to open this one and this one. I'm sorry, I opened the wrong two. Okay, here's the modern elegant JavaScript versus its equivalent Haskell, or its equivalent Racket. Okay, here's the function of three variables in Scheme. Here's the function of three variables. It's a very mathematical like notation. F is x, y, z goes to 5x plus 4y plus 3z. So that's the uncurried function. Here's the curried version of it. Here's the curried version of it in Scheme. You know, it's three fairly long lines of code. Okay, so this is what it looks like in Scheme, and this is what it looks like in modern JavaScript. Now I could write this in old-fashioned JavaScript, and it'll look much closer to the Scheme. Okay, and then here's how you apply in Scheme the triply curried function, and oh, I forgot to put that over here. Okay, so that's missing from over here. So here's how it would look like. Here, over here, it would look like this. Okay, here's how I would apply the triply curried function. It'd be f of c applied to 4. Then it returns a function which I give 5. That returns a function which I give 6. Okay. Okay. So it's just need these extra pair of parentheses, and oh, then I'm going to finish the alert. Okay. All right. So notice that how you had to say call the curried version with 4, get back a function, apply that to 5, get back a function, apply that to 6, but there's all these extra parentheses. Here it's, you know, it's a little bit cleaner. Apply the curried function to 4, get back. So this is a return function that gets applied to 5, and you get back, this represents the return function that's applied to 6. Okay, so it's not too bad. Notice it's not a whole lot worse than the uncurried one. There's the uncurried function, there's the curried one. Whereas in Scheme, there's the uncurried one. The curried one looks quite a bit messier. Okay, and then here's a partial application of the curried function. Oh, I wrote it the wrong way here. I wrote it as, I should have wrote that as the curried function with just 4. Okay. Give 4 to the curried function, and you get back g, which is a function of 2 variables. Give 4 to the curried function, you get back g, which is a function of 2 variables. Okay. If you give the curried function, well, this one, I would give the curried function the 4, and then give what it gives back the 5. That would be the equivalent of this one here. You get back h. The curried function with 4, what it gives back gives 5, and then that would be this one here. Okay. The JavaScript notation is really kind of nice. Here's how we took the original f and curried it as a function of 2 variables. So it's we take the original f and curry it as something that takes 2 variables and returns a function of 1 variable. So curry f is a function of 2 variables returning a function of 1 variable, and you need those 2 lines of code to do it. In JavaScript, it's really nice. I'm going to curry f from into something that takes 2 variable function and returns a 1 variable function. So it is something that takes 2 variables and it returns a function of 1 variable. Okay, so I get something much more compact than that. Okay, so the JavaScript notation for nested functions using these arrow operators is really pretty elegant. You know, they stole it from Haskell. You know, they skipped over essentially scheme and went from an old-fashioned C notation to this ultra-modern Haskell-like notation, which is kind of nice. Okay, if you were learning the JavaScript language, if you were decide to learn JavaScript, you could learn this really elegant language, this really elegant version of it. People sometimes refer to it as modern JavaScript, or its real name is ES6, if I remember right. Its name is ES6. Okay, ES stands for ECMA script. Okay, and this is the 6th version of Java. It's actually the current version of Java. I can't remember what the current version is, but that's the version that became that was the version of JavaScript that became this modern version. You could learn ES6, but the trouble is only a tiny fraction of the code out there in the real world is written as ES6 code. If you learned to program in ES6, you'd be fine, except when you had to read somebody else's code. Most JavaScript code is not written in this elegant form. Most of it's still written in the old-fashioned C-like notation. So you'd end up having to learn both. You'd have to learn the ultra-modern notation and learn the old-fashioned notation. And Java has the exact same problem. Okay. In this folder, where's the Java version? Oh, I didn't do a Java version of the currying. Okay, but if you go over here, if you look at the Java version here, that's the ultra-modern Java syntax. Today, I'll show you some of what Java looks like in the old-fashioned syntax. You could learn Java in its ultra-modern syntax, which is pretty much called Java 8. This is the syntax of Java since version 8. Trouble is, the vast majority of Java out there you have to read is not written in this elegant syntax. So just like the JavaScript language has a modern, elegant syntax, but not much code is written in it, Java also has a modern, elegant syntax, but not much code is written in it. So you're kind of stuck. If you wanted to use and learn the new syntax, you're still going to have to learn, you're going to have to learn essentially 2 languages, modern Java and old Java. And you have to learn modern JavaScript and old JavaScript. And it's actually causing problems in the real world because you're supposedly programming in a language called Java, and it's really, you're programming in 2 languages, modern Java and old Java. Oh, and C++ has the exact same problem. In C++, the new C++ is called C++11. And it's just like what we're seeing. There's this ultra-modern Lambda-like version of the language, and then there's the old-fashioned version of the language. You could learn the modern version. People refer to it as modern C++. Okay? Modern C++ means C++11, or what's come afterwards. It's almost like a new language, except that people write code in a mixture of the modern C++ and the old C++. They write code in a mixture of the modern JavaScript and the old JavaScript. They write code in a mixture of the modern Java and the old Java. And it's starting to become a problem. Because which language, you're learning 2 languages. Each one of them is now forked into essentially 2 languages, modern and old. And the code bases that everyone's using are now mixtures of the modern and the old. And they intermix. Everything that can be written in the old can be rewritten in the modern. Everything written in the modern can be rewritten in the old. They intermix. They're backwards compatible for the most part. Actually, some of it does not. Like some of the modern C++ cannot be written in the old version of C++. But for the most part, they're interchangeable. But you're reading 2 languages. You're trying to deal with, 2 very different languages in a sense. And I'll show you some examples of that in a minute. But like here, this is very ultra modern. This is very ultra modern Java here. Okay, it's just I could write this program in just a couple lines. I should write this in the old-fashioned Java for you to see what it looks like. and it's going to be like 10 times longer than this. Okay, so it's what are good ideas is to compare languages, compare, write everything in Scheme, write everything in Java, write everything in JavaScript. What is the core idea that runs across all the languages, like a closure? You know, what is the core idea? And then look at the details of how they implement it. Which one does it a little bit nicer than the others? Java closures aren't as actually powerful as Scheme and Scheme and JavaScript closures, because if you remember, we could write make adder in Java. We could not write make counter in Java. This one doesn't compile. Go back and remind yourself of that, but this one will not compile, and it cannot be made to compile. You cannot modify a variable in a closure in Java. Java has the limitations that when you have a closure, the variable in the closure is a constant. It must be a constant. You cannot mutate a variable in a closure in the Java language, but you can in Scheme and Haskell and JavaScript and many of these other languages. So they are not, they're not all the same. Even the idea of closure, there's some subtle distinctions between them. Java closures do not allow mutating variables inside the closure. Okay. Right now, let's look at sorting. Sorting is a nice example of, we started this the other day. This is a nice example of what it's really an example of is polymorphism and generics. And what we're really going to see is that closures are one way of dealing with the idea of polymorphism in generics. They're not the only way, okay, but they're a way. For example, Java, before it had closures, still had polymorphism in generics, so it had one way of dealing with this, and then with closures, you can actually deal with these things a little bit different way. Okay, so remember, here's the problem. I want to sort something. Here, I'll open it. I'll look at the Haskell version here. I want to sort this data structure. This data structure has got 5 entries in it, and it represents a country with its surface area and its population. And I can sort it all kinds of different ways. Sort alphabetically by the country name, sort numerically by the area, sort numerically by population. I could sort by area ascending, or I could sort by area descending. Okay. I could ask even then what happens if there's a tie. If I have 2 countries with the same area, which one comes first? Do I break the tie alphabetically, or do I break the tie by population? Okay, so you have all kinds of ways of sorting. So now, if you were doing this in a really old-fashioned language like Fortran, you'd probably have to write a bunch of different sorting functions. You write one that's sorted alphabetically, one that's sorted by area, one that's sorted by population. You might even have to write one that sorts, you have alphabetically ascending, and another program that sorts alphabetically descending. Then there's one that sorts numerically ascending by area. Then another one sorts numerically descending by area. You don't want to really write 12 different sort programs. You really want to write one sort and have it somehow be generic. A sort program that will sort in a generic way. So I only write it once, but it can sort any way I want. And so you need to parameterize the sort program. Now, you can do this in Java, and you can do this in C. For example, here was the sort function in C can be parameterized by a comparing function. You give sort a function that knows how to compare 2 items in the array that you're sorting. So you're sorting some array, okay, and the array has got items in it, and then the comparing function knows how to compare 2 items. And it'll tell you which one is the bigger of them. Now, bigger, I'm going to use bigger generically. Actually, I'll use the word smaller generically. The comparer will say, you give the comparer 2 items, you give it a pointer, you give it 1 item and another item. Notice that these are generic pointers, but you give the comparer 2 items and it returns an int. If it returns, the idea will be if it returns -1, this is the smaller. If it returns +1, this one is the larger. And if it returns 0, they're equal. Now you have to be careful. When I say that if this is -1, this one is the smaller, use that with a grain of salt. It's just saying that the comparison is, like if my comparison is by ascending order, the smaller one is the one that's smaller. If I'm sorting by descending order, the smaller one is the larger one. Okay, so it gets, yeah. So you have to remember if you're doing an ascending or a descending sort. So in a descending sort, the smaller one is the larger one. In an ascending sort, the smaller one is the smaller one. Okay, now this guy, he doesn't know if he's doing an ascending or a descending sort. So the comparator just says, I'm going to compare 2 items, and by definition, the one I call, when I return a -1, I'm saying this one is the smaller one than that one. So then you can write your sort algorithm using the comparator, and then the comparator, then you can sort your array any way you want. Now, if the comparator looks at then you can write the comparator to look at the string field. So then it sorts by strings. The comparator could look at the area field. So then you'll be sorting by area. The comparator could look at the population field. Then you're sorting by population. Okay, so that's what we're going to do. Now we're going to do that in Scheme. We're going to now Java has the same kind of thing. If you look up Java's sorting algorithms, I don't want parallel sort. I don't know why I got here. So I want to sort this generic array by this generic comparator function. So this comparator object is just like the comparator function pointer in C. C has a function pointer. Java uses an object pointer. It points at an object that is the comparator. Now, C is double. Notice, in the C case, you're actually doubly generic. This is an array of pointer to voids. So it could be a pointer to any kind of an array. And then the comparator takes pointer to voids. So you've got generics because of the pointer to voids, and you've got generic because you have an arbitrary function doing the comparing. There's 2 kinds of polymorphism there. Polymorphism over the type in the array, and polymorphism over the way you do the comparing. Same thing over here. The polymorphism over the type in the array is done by the generic parameter. That gives you polymorphism over the type in the array. Then this comparator object gives you your other type of polymorphism of different kinds of sorting. This thing decides how you compare 2 items in that array. Notice that in this language, what the comparator takes, type T, has to agree with what the array holds, type T. So if it's an array of T, you have to compare T's. That's where C, as an old language, falls flat. The comparator takes pointers to void. You're sorting an array of pointers to void. Nobody in the C world is making you agree on these things. This could be an array of ints, but this comparator can be thinking it's getting doubles. The comparator, you might get all mixed up in your coding. You may have written a comparator that compares doubles, but you're giving it to an array of ints. The compiler won't care. The compiler will happily pass a comparator of doubles to a sort of an array of ints. The compiler won't know the difference. The comparator won't know the difference either. When the comparators pass 2 ints, it'll just happily think that they're really doubles. You won't get runtime error. You won't get compile time errors. You won't get runtime errors. You'll just get bad answers, which may not show up for who knows how long before you realize that you got bad answers. That's why C is not a strongly typed language. Even though you have types on everything, it's really not a strongly typed language like people think it is, because you could have massive type errors in your C programs because of these pointers to void. C doesn't look past the pointers to void. So it's not what we would call a strongly typed language. The comparator could be given pointers to doubles. The comparator thinks it has pointers to doubles, but it could be passed pointers to ints, and the compiler won't know, and the runtime won't know. In Java land, the compiler knows. If you say that you're calling sort with an array of ints, you cannot pass it a comparator that's a comparator of doubles. The compiler will catch that. So you can't have a runtime error. The compiler would notice that. So there's a double generic. We're doubly generic. We're generic over the type in the array, and we're generic over how we compare them. Here, one level of genericity is covered by the pointers to void, and the other level of genericity is covered by the pointer to a function. Okay, now go over here to scheme. We have similar kind of thing. We're going to define a generic sort that's going to take a list. Now, scheme's an untyped language, so scheme's a little bit like Java, C. My function's going to take a list and a comparator, okay, just like the C and the Java. Okay, yeah. Oh, I'm sorry, wrong browser. Okay, sort takes a thing to sort, and then a comparator to sort to compare items with. Java takes a thing to sort and a comparator to compare items with. I take the thing to sort, which is a list, and the thing that compares items in the list. Unfortunately, in scheme, that could be a list of integers, and that could be a thing that compares doubles. And my program will blow up. You know, the compiler won't know it until I try to run it. So scheme is an untyped language, so I could muck this up. I don't have the type safety that Java gives me. Okay. On the other hand, a language like Haskell, which is a more modern functional programming language, it has the type safety of Java with the functional programming of scheme. Okay, so scheme, I could screw this up. I could make this guy a list of integers and make this guy something that compares doubles. Now, unlike C, my program will crash. Whereas in C, the program won't even crash. The program will just happily compare doubles as if they were ints, or compare ints as if they were doubles. In this case, if I did mess that up, the scheme program would crash. It would detect at some point that it thinks it's comparing ints, but it's really comparing doubles. Okay, so here's the thing I want to compare, and here's how I want to compare them. Okay, I'm writing a recursive insertion sort. I'm going to use nested functions. There's a function that called insert, and there's a function that does the recursive sorting. So there's the nested sort function that actually does the recursive sorting using the insertion function. Okay, now I nested these functions because they're really helper functions to the sort function. So the sort function needs two helper functions, one that does insertion and one does the actual sorting. And the sort function uses the insertion function as its helper. The sort function calls the nested sort function on the list. Okay, so if you read this carefully, what this is the begin. This is scheme's version of saying begin. Okay, so I have a begin statement where it's going to have a definition of insert, a definition of nested sort, and then it calls nested sort on the list. Okay, so it's the equivalent of, in our language, we would call begin. It's a block. Okay, lets you begin a scope. Okay, So now what does what does sort do? Sort is a function that takes a list and it asks, is the list empty? Because if the list is empty, if you sort an empty list, you just return an empty list. So if you ask it to sort an empty list, it just returns an empty list. Okay. Otherwise, it's a non-empty list. What the sort algorithm assumes is that the first item in the list needs to be inserted into the rest of the list. So the way insertion sort works is you give it a list and you say, okay, take the first item in the list and insert it into the proper place of the sorted rest of the list. Okay, so you sort the tail of the list, and then you insert the first item in the list wherever it belongs in the sorted tail of the list. That's a real elegant way to think of sorting. It's not it's an n squared sorting algorithm. It's not an n log n sorting algorithm. So it's an easy to write n squared sorting algorithm. It's not merge sort. It's not quick sort. It's an n squared sorting algorithm, but it's easy to write. Okay, so you insert into the sorted tail of the list the first item of the list. Now, how do you insert into a list? Okay, if you're going to insert an item into a list, here, this is a nested function. We're assuming there's an invariant here. A better way to put that is this is an invariant. The invariant is that list is already been sorted. I'm inserting X into a sorted list. Okay. Now I know that's the case because when I called insert, I inserted something into, I called sort on the tail, so the tail gets sorted before I do the insertion on it. So there I'm satisfying my invariant. Okay. So I'm going to insert X into a list that I assume has been sorted. Okay. What if the list is empty? Okay. Then you just add X to the list. If the list is empty and you want to insert X into an, you're just inserting X into an empty list. Okay. So if the list is empty, just add cons X or add X into the list. Okay. If the list is not empty, then we assume that it's sorted. So what we really need to know is the item we're inserting bigger or smaller than the first item in the list? If it's smaller than the first item, now here's what we call the net. See, there's our comparator that knows how to do the comparing. We compare the thing we're inserting with the first item in the list. If the comparator is true, that's what we call smaller. Okay. If this guy is smaller than the first item in the list, then he's cons at the front of the list because he's smaller than everything in the list. So he goes at the front. So if the comparer says that he compares with the first item in the list, which I think of as he's smaller, but remember the comparer is generic, so it could mean anything. Could be smaller, bigger. But if he compares with the first item in the list, he goes at the front of the list. If he doesn't compare with the first item in the list, which means he's bigger, then what you're going to do is you're going to cons the first item in the list onto the insertion of him into the somewhere further down the list. If the guy you're inserting is bigger than the first item in the list, then you bypass the first item in the list and you put him wherever he belongs in the tail of the list. So you cons the car of the list onto the result of inserting X into the tail of the list. Okay, takes a little bit of thought, but this is a real elegant way to write sort. Okay, it's a recursive sort. Now, I'm using, okay, notice that I'm actually using a closure here. If you look at this function, here's a function definition. In that function definition, I refer to comparator. Comparator is not a local reference. It's not a parameter of this function. Comparator is closed up here. So I'm implicitly using a closure here. The closure is letting me write very elegant, compact code. I don't have to pass the comparator to my insert function. Notice that the sorting function is given a comparator, but the insert function is not past the comparator. I don't put the comparator here. It's redundant. I don't need to put the comparator there. He can elegantly glom on to the comparator using the closure. He's nested inside of this guy, so the comparator is just that guy there. This is a common trick in functional programming, that the parameter to this function is going to be needed by the helper functions, but that parameter doesn't need to be passed to the helper functions. They just glom on to the parameter using a closure. So this is using the closure to that closure there. Okay. Now notice that this guy didn't need the closure. The actual sorting function isn't using the comparator. The comparator is only being used by insert. The recursive sorter calls insert, but he doesn't use the comparator. Okay. So this guy doesn't need a closure. This function doesn't have any non-local references. So it actually doesn't really need a closure. But the insert function does need a closure because the comparator is not local to him. Okay? Right? So there's two kinds. Now, remember in the Java and C, we have two kinds of genericity. There's generic array compared by a generic function. Okay? And in C, or in Java, we have a generic array compared by a generic function. Over here, we only have a generic function. The other level of genericity comes from the fact that Scheme doesn't care what's in this list. All lists in Scheme are generic lists. Scheme's an untyped language. So I can make that a list of integers, I can make that a list of doubles, I can make that a list of countries. As long as whatever's in that list is what this comparator knows how to look at. So this is by default generic, because Scheme, like JavaScript, the lists are just untyped lists, so they're essentially generic by default. They're generic by default. Like whereas in Java and C, arrays are not generic by default. An array is either an array of int or an array of doubles or array of strings. But here, the function takes a generic array. So it could be an array of ints or an array of doubles, but it's still an array of ints or an array of doubles. Same with Java. An array is either an array of ints or an array of doubles or an array of strings. Here, I'm saying, it can be either an array of strings or an array of doubles, one or the other. In Scheme, it's actually very messy. This list could be a mixture of ints and doubles. Scheme doesn't care, but my comparator will care. It's up to me to make sure that this comparator matches up with what's in that list. So I'm going to write a comparator for countries. And then I'm going to give this thing, I'm going to sort an array of countries, but it's up to me. This is where Scheme is a more old-fashioned language. It's kind of weak like C is. It's up to me to make sure that that comparator and that list agree with what they're doing. If that's a list of countries, that thing compares countries. If that's a list of integers, this guy should compare integers. It could compare them in ascending order, it could compare them in descending order, but it's up to me to make sure that whatever I put in here, this thing knows how to compare. So that's where this comes in. I'm going to compare X with the car of the list. So compare has to know how to look at whatever's in the list because it's past the car of the list. It's given an item from the list, so it better know how to compare them. So it's up to me to make sure this guy agrees with this guy. But I am doubly generic. I can put anything in that list, then I can compare them any way I want. But it's up to me to make sure that these two guys agree with each other. Okay? Now I'm going to start building my comparators. This is where things get a little bit interesting. I want to sometimes compare countries by this field. sometimes compare them by this, sometimes compare them by this. Sometimes I want to compare them by area, but in an ascending form. Sometimes I want to compare them by area in a descending form. Okay? So here's what I'm going to do. I'm going to define a function that makes comparators. I'm going to build these comparators on the fly. I'm going to make a function that makes comparators. Okay? Now, a comparator is a function that takes two items and tells you which is the larger of them. A comparator takes two items and returns either true or false, depending on which one of these is the bigger of the item. You know, it returns true to mean like, or smaller, whichever way you want. Like here I said, if this thing returns true, this is the smaller. If this thing returns false, this is the larger. And if they're equal, it'll return true. Okay? So I'm going to build comparators. Okay? So I'm going to write a function that returns a comparator function. So here's a function that returns a function. Oh, I'm sorry. Well, here's a function that takes in another function and returns a comparator function. So what I'm defining is a parameterized comparator. I'm going to make a comparator. I'm going to write a function that takes in something, and then it returns a closure. Okay. Now here's what it does. Make comparator returns the comparator. Comparator takes two items and it compares them. The comparison is actually this guy. Okay. But I'm comparing the area. See, this thing out of a country gets the area field. This is a get method. Get area out of a country. The area is the, see, this is a list. The area is the second item in the list. So it's the car of the cooter of the list. It's the, see this little tricky guy here? You read that as the car of the cooter. It's just an abbreviation. It's the car, the first item of the second of the tail of the list. If this is my original list, it's got 3 items in it. The second item is the first item in the tail of the list, the car of the cooter. On the other hand, the population is it's the third item in the list. It's the second item in the tail of the list. It's the car of the cooter of the cooter. Okay, so it's the car of the cooter of the cooter of the list. People had fun writing this kind of code back. Not many people write scheme anymore. There's a fair number of people who use scheme a lot. So these words, remember, were invented back in the 50s. Car actually stood for content of address register, and cooter stood for content of decrement register. They were named after registers that held the values in the CPU. And people get used to talking about cars and cooters, and car means the first item in the list. Cooter means the tail of the list. Okay. If I want the second item in the list, that is the first item in the tail of the list. So that's the car of the cooter. If I want the second item in a list, that is the car of the cooter of the cooter. Because you take this list and you peel off its tail. Then out of that list, you have to peel off its tail, but its tail is a list. Then you have to take the car of that list and you get that item there. Okay, so you get this. So I abbreviated that to be get area is the car of the cooter of a country, and get population is the car of the cooter of a country. So this is a get method. Get area, get area. And then compare them by whatever this comparator is. So this is a function that actually does the comparing of those two items. And then here's how I compare by area descending. I pass the less than function into here. If I pass the less than function into here, I'm doing a less than comparison here. If I pass the greater than function into here, I'm doing a greater than comparison. So I'm sorting descending and sorting ascending here. We run out of time. So notice that this is tricky code. Okay, this is tricky code, and this is what modern programming looks like. And I'm going to show you the Java version of this. The Java version, we'll go through the Java version of this on Monday. It's almost nightmarish. Just real quick, here's the Java version. There's actually about 7 or 8 different Java versions, because Java has no actually really well-defined way to do this. So you can do this code using anonymous inner classes, classes, interfaces. There is the ultra modern Java way of doing it. We'll look at the ultra modern Java way of doing it. No, I'm sorry. No, I'm sorry. This one's the ultra modern Java way of doing it. This is going to be the ultra modern Java way of doing it. And then there's all these various older Java ways, but no one older Java way of doing it. It's just kind of weird how when you want to do generic sorting in Java, it's a bit of a nightmare because nobody agrees on what's the actual right way to do it. There's so many styles of Java programming that have accrued over the years. So there's actually 1, 2, 3, 4, 5 different ways, 6 different ways there. Plus, there's a couple different ways in these folders. Okay, so we'll look at what Java does to try to get a generic sort. How do you get Java to do what it knows how to do? It knows how to do generic sorting, but it's still a really big mess in Java to get this sorting. And basically what we're doing is we're doing a bunch of different ways of doing some kind of closures, some kind of nested. It's all going to be similar to the racket code. The racket code is actually the model for what we want, and then Java wants to mimic this model somehow. And there'll be closures buried in the Java code in different ways. Okay, so look at this code. You can download this code, study it. It's very interesting code. You'll see once you get into the real world and start doing some real world Java, you'll see how you have to do this kind of stuff pretty often. This is a nice example of the kind of hairy Java programming that you need to do. And if you want to know why Java created modern Java, it's because this is a mess. And this is the modern version of it, which if you program it which got motivated by Scheme and Haskell. The ultra modern Java version is very nice, but not many people write it that way. Not many people yet are writing things the ultra modern Java version. They're still writing things in mostly the older Java version, which is kind of a royal mess. And the royal mess motivated trying to move towards this kind of elegant code. And this elegant code is not trivial. This is still not trivial to read, but it's still way better than the old-fashioned Java way of doing things. Okay, so that's what we'll do on Wednesday. We'll play around with these. Read this code. It's interesting code, and this whole course is really trying to get to why old-fashioned Java wants to be replaced by modern Java. And all the stuff we've done over here, learning how to do closures, is really learning how to move from old-fashioned code to new code. Okay, so I'll quit there because we ran out of time. Okay. So if you have questions, please send me an email. If you have questions, look at that code, look at the Scheme code, and look at the Java code. Compare them. It's an interesting comparison. It's a challenging comparison, but it's real important. It's what a large chunk of modern programming looks like these days. Okay, so see you on Wednesday. And if you have questions, send me emails. Bye.